Okay, so let's talk about adding vectors. If I was to tell you I walked 3 miles east and then 4 miles north, and then asked you how far away am I from where I started, well, you would know that, okay, I've walked 7 miles total, but I'm not 7 miles away from where I started because I've changed directions. Okay, so the proper mathematical way to handle this type of situation is with vectors, right? That's why we're going to use vectors extensively in this class, because vectors can handle things that can change directions. Okay, so I draw one vector to represent my first statement. I walked 3 miles east. Right, so the length of this vector corresponds to 3 miles, and the direction points in the east direction. Then I draw another vector with the length corresponding to 4 miles, pointing north. And you can see I've drawn these tail to head. The tail of this vector is on the head of this vector. And this is how we're going to add vectors with something called the tail to head method. And so you can tell that, okay, I started over here, I finished up here. So how far away am I from where I started? Well, that's the length of this purple vector here. Okay, which we're going to in general call the resultant. Anytime you add two vectors together, that added together vector is going to be the resultant. Okay, and here we have a triangle because I walked east and then north, and east and north are always perpendicular to each other. So I have a right triangle. I can use the Pythagorean theorem to figure out the length of that purple vector. Right, that length is going to be the square root of 3 squared plus 4 squared. Right, and this ends up being 5. Okay, so the length of this vector is 5. I'm 5 miles away from where I started. So that's just our first quick example of adding vectors. Let's do this in a few more cases. So in general, as I told you, we're going to use what's called the tail to head method to add vectors. So let's start with two parallel vectors. I have vector A pointing in what I'll call the plus x direction, and vector B also pointing in the plus x direction. So if I want to add these two together, I'm going to take the tail of B and I'm going to place it on the head of A. Okay, that's what I've done here. I've taken the tail of B, placed it on the head of A. And now if I want to know what is these two vectors added together, well, I'm going to draw a new vector which starts at the tail of A and points to the head of B. And so that's what I've done here on the next step for the purple vector. So my resultant vector, which I'll call R here, is just this one long vector. Okay, so there's lots of examples of situations where this could happen. You could have two different people pushing on a box, right? Both pushing in the same direction. The net force would be some larger force than either person is pushing with, right? Another example I wrote in here, you're walking 5 miles per hour up an escalator, which is also moving up at 2 miles per hour. Right? So you have an escalator with some velocity, 2 miles per hour, that's corresponding to this vector B, and then you're walking up the escalator with 5 miles per hour velocity relative to the escalator. Well, somebody to the side of the escalator is going to see you walking even faster. They're going to see you walking 7 miles per hour because both you and the escalator are moving. Okay, so that's two different examples of where vectors could come in handy. Let's do another example. This time we're going to do the tail to head method with two vectors which are not parallel. Okay, so again, I have A plus B. I want to take the tail of B and place it on the head of A. Right? I'm free to move these vectors around wherever I want to. So I can move vector B such that its tail is placed on the head of A. And now I want to draw the resultant vector now. I again want to start where I started at the tail of A and point a vector to the head of B. And so that's what I've done here with the purple vector. Okay, so that is my resultant in this case. So in this case, if one person was pushing on a box in the direction A is pushing, and a different person is pushing on the box in the direction person B is pushing, well, the box isn't going to move in either this direction or this direction, right? It's going to move somewhere in between those two directions, and ends up that direction is given by this purple vector. Okay, so that's another nice example. What if I was to do this in a different order? What if I asked you what is B plus A? So let's try that. I take the same exact two vectors, but I'm just going to do B plus A instead of A plus B. So this time I'm going to take the tail of A and I'm going to place it on the head of B. And again, I'm going to start where I started at the tail of B and draw a vector which points to the head of A. Okay, and so that's what I've done here with the purple vector. That is my resultant. It's the same answer as, oops, let me go backwards. It's the same answer as we had in the previous case. Right, so it turns out that A plus B is equal to B plus A with vectors. Okay. What if I had two vectors which are anti-parallel, two vectors which are pointing in opposite directions? Okay. well, the tail to head method still works. If I want to add these two vectors together, I take the tail of B and I place it on the head of A. Okay, that's what I've done in step 2 here, right? I've taken the tail of B and placed it on the head of A. And now if I want to know what is my resultant vector, again, I need to start where I started, right here, and draw a vector which points to where I'm finishing with that final, the head of B. Okay, so this is going to be my resultant vector. So that's what I've, again, done here in the third step. Okay, so that's a nice example. And this is, we can, again, come up with other examples of when this would be relevant. You could have two people pushing on a box, one pushing to the right, right? That person is pushing to the right. This person is pushing to the left. What direction is the box going to move? Well, it's going to move to the right because person A is pushing harder. Okay. Another example is what I have written down here on the bottom. Let's go back to the escalator example. Let's say you're walking 5 miles per hour up an escalator, but that escalator is moving down at 2 miles per hour. So don't try that in real life, you'll get in trouble. But of course, it's going to appear to somebody to the side of the escalator as if you were moving at 3 miles per hour, right? So if we solve these problems in class, so let me go back here and get my pen working here. So in general, we're going to draw a coordinate system. I'm going to define, for example, this to be the plus x direction, right? And then vector A is in the plus x direction, vector B is in the minus x direction. Okay, so with vectors, positive or negative direction is really going to matter also. Okay, and so vectors properly handle that for us. Okay, one more example of the tail to head method, and this is why I like the tail to head method so much, is because it works really well no matter how many vectors you have. Okay, so if I want to do A plus B plus C, I do exactly the same method. I first take the tail of B, place it on the head of A, right, which is what I've done right here. I've taken the tail of B and placed it on the head of A. And so this is A plus B. I could draw in A plus B. A plus B is this vector, right? It starts at the tail of A and points to the head of B, right? So this is A plus B right here. And if I want to do A plus B plus C, well, I just have to add C to my vector A plus B, right? So I start at the excuse me, I take the tail of C and I place it on the head of A plus B, and I get this vector here, right, which is going to be A plus B plus C, right? I start at the tail of A and points to the head of C, okay? And so that's what I've drawn in here in full detail with the tail to head method on the right, okay? So the tail head method is going to work no matter how many vectors you have, okay? Let's go back to this example from the Florida road trip that we talked about in the last video. If you were to start in Tallahassee, drive to Jacksonville, take all these different steps, I could represent each of those steps with a displacement vector, vector A, vector B, vector C, vector D, and then vector E. If I draw them all tail to head, which I've done here, right, take the tail of B, placed it on the head of A. So effectively what we've done here is add A plus B plus C plus D plus E. And then in the end, we end up with our resultant vector where we start at the tail of A and we point to the head of E, and this is our resultant vector. Okay, so this is a displacement vector which is going to tell us where we are when we finish relative to where we started. Okay. Just to let you know, there's an alternative method to add vectors. It's called the parallelogram method. Just to go through that real quick, your book goes through this in a little bit more detail. I really prefer the tail to head method to the parallelogram method, but whatever works for you is okay. Okay, so with the parallelogram method, we're going to take the tail of B and we're going to place it on the tail of A. Excuse me. So I'm going to draw both vectors tail to tail. I'm then going to draw a parallelogram. So I'm going to draw a line parallel to B. I'm going to draw a line parallel to A. Okay, and in the end, I'm going to start with a vector whose tail starts at the tail of both of these vectors and which points to the opposite corner of the parallelogram. Okay, so that is going to be A plus B. Okay, and so that's what I've drawn down here on the bottom. So the parallelogram works just as well. Whatever works well for you, please try it. Okay, what about subtraction? Well, to do subtraction, we're still going to use the tail to head method, and we're going to rely on one of the rules about vectors that we learned about in the last video. And that rule is that if you negate a vector, you're just switching its direction. So if I have a vector b here, if I want to know what is negative b, that is just flipping that vector around, right? It's anti-parallel to b. Okay, and now I can use the fact, right, that a minus b is the same thing as a plus minus b, right? And I know how to add vectors, right? I know how to add a plus minus b. So if I have minus b, I've drawn that right here, I can just, again, now use the tail to head method with a plus minus b. So I draw an a, I take the tail of minus b, I place it on the head of a, and then I start with my resultant vector being starting at the tail of a and pointing to the head of minus b. Right? This is my a minus b vector here. Okay. What if I asked b minus a? Is it the same thing as a minus b or not? Let's check. This time I'm going to find what is minus a. So minus a is just flipping around a. So it points anti-parallel to a. Now I take the tail of minus a and place it on the head of b, and I get this kind of picture here, where again I draw in my b minus a by drawing a vector whose tail starts at b and points to the head of minus a. And you can see, let me flip to the next slide here, that I don't get the same thing, that a minus b is going to be different than b minus a. Okay? And in fact, a minus b is anti-parallel to b minus a. So they're both pointing along the same line, but in opposite directions. So I can note that in general, with vectors a minus b, it's going to be equal to minus b minus a. Okay. So in the next video, we'll learn how to do this more mathematically instead of just with pictures.